Okay, now it is good. Just make it full screen.
Cool, cool. Thanks, Pap. Uh, so good afternoon to all the esteemed guests present there. My name is Ashutosh Kumar Tripathi, and I'm working in Electronics and Communication Engineering Department here at IIT Roorkee. Currently, I'm exploring spin transport in organic LEDs and trying to extract insights from biological systems to put in here and might be improving the efficiency. So currently, I'm working on a candidate molecule called ALQ3. So why I have selected ALQ3 is because like it is widely used while manufacturing early OLEDs and like low cost displays. So it is fluorescent. So but its fluorescence is restricted to the spin statistics, which is it can utilize only the 25% of available excitons. Uh, so it is usually a green emitter, emits light at 512 nanometer peak. Apart from that, it can function both as an electron transport material and as an emissive layer too in OLEDs. And as I said about the efficiency, now the motivation behind this study is because fluorescent OLEDs are cheapest and like they will benefit us environmentally, but they suffer from low exciton loss and also the triplets tend to stay for long. So the triplet accumulation occurs, which basically is very much detrimental for the device health. So we adopted to other strategies such as we use phosphorescent OLEDs where we use heavy metal complexes which have environmental concerns for sure, but the plus point is that we can use almost 100%, like all the triplets also can be put to use. The stability, of course, it depends on the dopants. And then there are more recently explored TADF OLEDs, which are moderate in cost, but they are very complex to produce. So some fundamental questions arise out of it. Are there some techniques which can improve the performance and stability of fluorescent OLEDs? And can some triplets be converted so as to utilize the efficiency of these fluorescent OLEDs to their maximum? Now, these questions are very important if we take into consideration the environmental concern, the ease of synthesis, large-scale manufacturing, and availability throughout the globe. So here, electron transport through biomolecules and chiral nanostructure comes to our rescue. So recently, a very much explored phenomena is chirality-induced spin selectivity in solid-state organic molecules, uh, which had been introduced in 1990s as well, where electron transport through biomolecules was reported to be spin selective. What spin selectivity means is certain spin states are they are promoted in a certain direction, and the other spin states are promoted in the other direction depending on the chirality or the handedness of the molecule in through which they are transmitting. So because chiral molecular structures, they break inversion symmetry, so this spin selective filtering is it is reported to be because the electrons orbital angular momentum couples with the spin angular momentum. So certain spin orbit type coupling, but not fully spin orbit coupling. So you can also think of it when a charged particle is subjected to a magnetic field, it undergoes circular motion. So similarly, if a charged particle is forced to go in circular motion, it is as if an effective magnetic field is being applied to it, which is interacting with its spin states and promoting certain spin state in one direction while promoting other in the other direction. So like uh, there are lots of applications which are being explored for this phenomena, such as chiral molecule detection, photovoltaics, and molecular spintronics. And what we are working on currently is organic LEDs, which are green LEDs. And then we have quantum spintronics and chiral qubits. So lots of work in going on across the globe to harness this technology in various domains. Now, introducing CIS in ALQ3. So uh, I would not like to go deep into it because there are some manufacturing things that we can do with ALQ3 to make it more chiral. But given the time constraints, I would not like to go deep into it. But I will just tell you that we rotate the substrate 5 to 10 degrees and we spin coat it. So while the substrate is evolving, it basically the individual molecule of ALQ3, though it is not chiral, but a supramolecular packing assembly makes it chiral. So this is GLAD, and I mean this is the most effective technology for introducing chirality in ALQ3. The other are basically mixing chiral additives to ALQ3 and that basically enhances the chirality. So 5 to 20% in weights of chiral additives are added while vaporizing AlQ3 into the substrate. And the third one is ligand modification, where the electronic structure of AlQ3 itself is changed. Some C3, C5, or some sites uh, asymmetry is introduced in some sites so that the overall structure doesn't remain symmetric. So in that sense, we can introduce chirality. So the best method is GLAD method, which has been reported. So what is the result? So result is, as you can see on your screen, a helical type pattern where not layer by layer, but now a helical type pattern grows. So if we talk about the overall packaging, molecular packaging, it shows some chiral nature. And with this, we can create a chiral OLED where the central emissive layer is chiral. The central layer is AlQ3 and it's chiral. So electrons and holes, they are sort of moving through the molecules. They experience certain degree of spin selectivity. So spin studies in OLEDs, spin based. How do theorists view the challenge? So as you all know that in organic molecules, the energy levels are discretized. So there's no band of energy level. It does not exist. So the electrons, they can transport by hopping from one energy level to the other. So we'll try to club cis with polaron hopping mechanism, which is seen in OLEDs. So some basic assumptions that we'll make is the spin selectivity of chiral channel is such that it preferentially allows only the down state to move forward, and for recombination, subsequently the up state will be preferred. So, and the average, we also make another assumption that the average hyperfine axis of the individual polons which are being experienced by them, it aligns at small angles to the transport axis, which is being the axis through which the electron is getting transported, as well as to the externally applied magnetic fields, which we use to probe the spin states. So, first of all, generation of polons. So we have environment and we have two AlQ3 molecules which are neutral, and both the electrons are paired. They are in their highest occupied molecular orbitals. Now, due to electrical excitation, what happens is a certain spin goes from the higher HOMO level to the LUMO level of one AlQ3 molecule. So that spin can be downspin or upspin, as you can see. Now, to neutralize the ground state, another adjacent polaron has to transfer an electron. But because of spin selectivity, now both the spin states can't move forward. So spin selectivity imparts certain momenta to the certain spin configurations. So as here we have assumed that downspin will move forward. So downspin makes a transition from the HOMO of neutral AlQ3 to the HOMO of the excited AlQ3. And here we have two spin states possible. So now this initiation of polarons in singlet, triplet, or T plus state is gets enhanced. As you can see, there are two other spin states also which are forbidden, which is when up state makes a transition. Now, when up state makes a transition, either it can generate an excited AlQ3 polaron with another AlQ3 polaron, or else it can just make the ground state of AlQ3 both polarons not excited basically in the. So in this case, T minus and singlet and T naught, they won't form, they'll form in less proportions because of the spin filtering of the channels. So yeah, now what happens once we have these both polarons, now the unpaired electrons in both polarons, they can exist in a superposition of state. This can be either up up, up down up, or down down. And they exist in it while interacting with the internal hyperfine fields, as well as with the externally applied magnetic fields, which is changing their spin state. So they are in superposition basically. Now we'll to discuss the kinetics of it, we come to the polaron hopping mechanism, where the polarons can be thought of as spins precessing around their individual hyperfine axis at site alpha and site beta. So there are two sites and there's an environment. So now what happens is polaron at site alpha, which is near to site beta, it has two choices. Either it can hop directly to the environment with separation rate, Ks separation and Kt separation. So such a polaron will not contribute in generation of light, but it will get separated. So it will contribute in the generation of current through the device. Or else if the polaron is provided it is in a singlet configuration, it has another choice to make a jump from site alpha to site beta, forming a bipolaron. And this can happen with the rate Ks recombination. Now, once the polaron makes a jump from site alpha to site beta, if the bipolaron retains its singlet character, so it will make a transition from like excited state to ground state and give out photons, which is basically visible to us as lights. But if it anyhow gets converted to triplet character, again the direct transition is not possible. So it will have one choice, which is to uh, hop from side beta to the environment. So in this sense, it is getting injected to another pair of polarons, but now the site alpha is vacant. So now another polaron can make a transition from environment to site alpha with the rate of K injection, which is the charge carrier injection rate. And it will be like in a particular spin state of the four available to us, with span or spin basis. So now in the recombination event also similar thing occurs, because the down spin was promoted in one direction. In recombination events, up spin states will be promoted. So it's all illustrated here. So when up spin makes a transition, certain spin states are promoted over the other. When up spin is making a transition, uh, T plus and singlet and T naught states are much likely to be formed rather than T minus and some portion of singlet T naught again. So the action of cis is captured in the projection operators that we use. So we modify the projection operators a bit, where we like add certain population to the down state while the forward path is going on. As you can see here, sin chi is added to the up down state, and sin chi similarly is subtracted from the down up state. Now, if you plug in chi equal to 0, you'll get your same singlet triplet projection operators. But this is to show certain bias towards the spin states while being transported. So again, as like we can specify the state vectors and make the projection operators out of it, and we can do the reverse for the recombination, which is like the transport of electron in the opposite direction, where we extract spin states from the down state and provide them to the up state. Now we use these projection operators in our modified Lindblad equation, which is like generally used for solving open quantum systems. There's one more term that we need to include in order to get realistic results, which is phonon-assisted decoherence, where a polaron can couple to local lattice distortions, and it can introduce fluctuating local fields, which are called phonons, which will produce scattering events that will randomize spin phases. And what happens is now the singlet triplet states, the coherence which exists is no longer governed solely by hyperfine interactions. So the scattering will accelerate decoherence, which will in a sense shorten the lifetime of the polarons which are available to us. So some mathematics, like I would like to skip it, but for now, but yeah, we have Zeeman hyperfine exchange and dipole interactions taken into consideration, and a spin Hamiltonian will govern the time evolution of the system. Now, as like the polarons are initially made electrically, so like they'll be initiated in a maximally mixed sense. So our initial state is iota upon 4z, where z is the dimension of nuclear subspace, the amount like the spin subspace of nuclei of the bath in which the polarons are interacting. Now the extended master equation has four terms. The first term is the commutator term, which describes the coherent evolution of the system. The second term with anti-commutator relation are basically with respect to the decay of the population states from singlet and triplet channels. And these are the very specific PS and PT, which will get biased due to chirality. Again, we have decoherence term also at with rate kph, and this lk and lk dagger. These are basically the operators through which our system is coupling with the environment. And then at last we have the injection rate, and this is all attributed to the polaron hopping mechanism. And at last we evolve the roti in time. We evolve the system get roti, and then if you want to get the expectation of singlet, that can be found out by applying ps into roti and taking the trace of it, which is standard density matrix operations. And when we get this expectation of singlet or triplet at any time, we can integrate the time average out of it and multiply it with rates to get the recombination yields. Now, through recombination yields, we can extract out meaningful parameters. The first is magnetoconductance, where the separation phi s and phi t separation yields will come into account, because these are the yields which are basically contributing to the electric current through the device. And the amount of photons released to the device is like attributed to the recombination event. So we plot in the recombination events as such. And this is the structure of AlQ3 molecule, and the hyperfine environment can be found out readily from the literature. So these gray, shaded in gray, are the nuclei which we use in our computation.
I'm sorry, we have time for your last slide, so if you jump to it, we would be very
Okay,
grateful.
so yeah. So we I extracted the MEL with magnetic field strength. So here we try to like find out the window, best window in which the performance of this device can be enhanced. So we found out that for normalized magnetoelectroluminescence condition, when there is no decoherence present in the system, the best window is from pi by 6 to pi by 3. Similarly, we introduced a realistic uh, decoherence rates attributed to the LQ3 molecule, and we find out the best window to be near pi by 6 and near pi by 3. That is where the selectivity should be biased in order to achieve maximum strength. And similarly, we did for magnetoconductance and magnetic field strength as well. Since the time is not there, I won't discuss it much further. But again, uh, uh, chirality is seen to enhance the performance of the device. That's a thing. But increasing chirality also gives rise to a surge of triplet states, which is very much critical for the device operation and its stability in the long run. So to conclude, we identify a parameter regime for enhancing optical and electrical activity of chirality-based fluorescence OLEDs of future. And then, but again, there are some stability issues in thin film parallel OLEDs which have to be taken into consideration. And we actively look for scenarios where more and more of dormant triplet states can be utilized in order to contribute to the magnetoelectroluminescence or the magnetoconductance for sensing purpose. We are hopeful that the next breakthrough in enhancing fluorescent lighting and sensing will come definitely from biology, where the system has to choose a pathway out of multiple possible pathways. And these are the potential applications. It can be used in magnetic field sensing for biological applications, pharmaceutical chiral separations also, and then optical encryption, quantum communication, and plethora of applications can be there. Again, I would like to end my talk by saying bioluminescence is a phenomena which is not yet explored in that context, in the context of the spin states of it. So maybe I'm very much hopeful that bioluminescence will give us some insights which we can utilize in our fluorescent devices and make them more readily available and more efficient for the masses to use. So may Mother Nature continue to inspire us, and thank you if you have any questions.
Thank you very much, Ashutosh. This was really intense.